Greetings, dear learners. Welcome to the official YouTube channel of SRN International School, Jagatpura, Jaipur, Rajasthan. I am Faculty of Chemistry at SRN International School. In this video, I am going to explain the chapter 6 Thermodynamics of grade 11th Chemistry from NCERT textbook. Thermodynamics is the branch of science which deals with the study of different forms of energy and the quantitative relationship between them. So there are certain basic terms and some important terms and definitions in this chapter of thermodynamics. So let us go with the basic terms. In thermodynamics, thermo means heat and dynamics means movement. This movement is in the form of radiation or in the form of processes. So the direction of heat flow will always be from hot to cold. And that when we come with the term as thermodynamic equilibrium, it means that objects are at same temperature. The temperature is actually the measure of relative hotness and coldness. Now there are certain basic terms like system. Now system is anything in thermodynamics which is under study in terms of heat or in terms of energy. When we say open system, then in this open system there will be always an exchange of mass and energy. In the closed system, only there is an exchange of energy, whereas in isolated system nothing can be exchanged. Like in the case of thermos or thermos flask, if we keep a hot coffee, then there will be neither be the exchange of matter with the surrounding, and also there will be no exchange of heat. That means heat will be remaining inside the thermos flask, so it will not be exchanged with the surrounding. There are certain important terms like extensive property. Extensive property is such a property in thermodynamics that depends directly on the size of the system. And for example, volume, mass, mole, etc. Intensive properties are the property that does not depend on the size of the system. For example, density, temperature, and molarity. There are certain terms like state variables. State variables in a system is a system which can be described by its measurable properties. So like for example, temperature is a state variable because it varies. At one time it is very, cold and it becomes hot. So there is a variation in the temperature. Pressure, volume, these are all is considered to be state variables of the system. State function is a property of the system that depends only on the state variables and hence only on the initial and final states of the system. So that is the state function. Now, for example, enthalpy, entropy, free energy, volume, pressure, temperature, these all are termed as the state function. So it is a property of the system. Then path function is a thermodynamic quantity that depends on the path. For example, work done. So as we were talking about system is anything which is under study. So apart from the system, the rest of the part is called as surrounding. And in thermodynamics, system and surrounding makes up the universe. For example, if there is a beaker in which a reaction is going on, and in that reaction, we have to study how much amount of energy is being liberated, is it released or it is absorbing. So this is under study and therefore this becomes a system. Apart from this system, the rest of the part of which is the environment we can call is the surrounding. And this system and the surrounding makes up the universe, And this is always we are talking about in terms of thermodynamics. That means we are studying about the energy, about the heat. Now, we talked about the state function also. So, state function is the property that depends upon the initial state and final state and not on the path as to how the initial state has come to the final state. So, one of the state function is internal energy represented by a symbol U. So, what is internal energy? Internal energy of a system is the sum of kinetic energies of all its constituent particles plus the sum of all the potential energies of interaction among these particles. So there is a system, like for example, as shown in the figure, that there is a cylinder containing gas. Now, this internal energy of this system, which is under study, will be the sum of kinetic energies of all the constituent particles of those gases, and also the sum of all the potential energies of interaction among these particles. So that is the total energy of a system of its own is the internal energy. So if the internal energy is U, initial internal energy is taken as U1 and the final internal energy is taken as U2, then the change in internal energy that represented by delta U will be equal to U2 minus U1. And therefore it is a state function. First law of thermodynamics. First law of thermodynamics states that energy can neither be created nor destroyed, although it can be changed from one form to another. So this first law of thermodynamics is the application of the conservation of energy, and it is a principle given for heat and thermodynamic process. The change in internal energy, that is delta U of a system, is equal to the heat added to the system minus the work done by the system. So Q is the heat, Q amount of heat is when is added to the system, and this Q amount of heat is being used in doing the work done. Then when system will be doing the work done, then this Q minus W will be equal to change in internal energy. So delta U will be equal to Q minus W. And thus the amount of heat that has been added to the system is being given out in the form of work done. Therefore, energy is neither created nor destroyed. So this is the first law of thermodynamics. Enthalpy. Enthalpy is another state function. And what is enthalpy? Enthalpy is the sum of internal energy and pressure volume work. It is given by the symbol H. So it becomes H equals to U plus PV, where U is the internal energy and PV is the pressure volume work, that is work done by the system. Now, the change in enthalpy, which is given by delta H, will be due to the heat absorbed or heat released. So there will be change in enthalpy, delta H, which will be equal to delta U, where delta U is the change in internal energy, plus P delta V, where P delta V is the work done by the system. So enthalpy is the amount of heat or energy absorbed by the system to cause the change in the system or released by the system so that there may be a change in the system. So if delta H is positive, that is greater than 0 means positive, then it is an endothermic, that means absorption of heat is taking place. But if the delta H is less than 0, that is it is negative, then it is an exothermic reaction where there is a release of heat. And this reaction processes will be a spontaneous. Enthalpy changes when we talk about, then enthalpy is a state function whose value depends upon initial and final state, and for a particular system it cannot be measured. So therefore we have to measure the enthalpy change, that is delta H, because it depends upon the initial and final state and not on the path of the system. Since delta H is H final minus H initial, so the enthalpy change for a chemical reaction is found to be delta H reaction, whereas delta H reaction is the enthalpy of reaction, which will be equal to H product minus H reactant. So enthalpy of reaction is also called as heat of reaction. So there are various types of enthalpy changes. Enthalpy changes during phase transformation. When we talk about enthalpy of fusion, that is change in enthalpy of fusion, then it is delta fusion H. But when we put naught on it, that means delta fusion H naught. So naught denotes standard enthalpy of fusion, and standard enthalpy of fusion means the melting of a solid is taking place at STP. So STP is standard temperature and pressure. So, and that is for 1 mole of a substance also. So now enthalpy fusion is defined as a change that is taking place during the fusion of 1 mole of solid at its melting point. Similarly, enthalpy of vaporization, delta vaporization, VAP, H naught, is the change that is taking place during the vaporization of 1 mole of liquid at its boiling point. Some special enthalpy changes is like delta H reaction, which is heat of reaction, then delta H solution, that is heat of solution. So it is the enthalpy change which is associated with dissolving a solute in a solvent. Then delta H combustion, which is heat of combustion. It is an enthalpy change associated with burning of 1 mole of substance in excess of oxygen. Similarly, enthalpy of vaporization, which we have already done, it is enthalpy change associated with liquid turning to vapor. And enthalpy of fusion is also enthalpy change associated with solid converting to liquid for 1 mole substance. And enthalpy of formation, that is delta HF, is the enthalpy change that is associated with the formation or preparation of 1 mole of substance from its elements. Hess's law of constant heat summation. It states that for a chemical equation that can be written as the sum of 2 or more steps, the enthalpy change for overall equation is the sum of the enthalpy changes for the individual steps. For example, if A reactant is converting into B in one step, then the enthalpy that is considered as to be the change in enthalpy would be delta HR, where R is the reaction. So for A converting to B, delta H reaction would be equal to the sum of the enthalpy changes taking place in different steps to form the product P. So A is converting to B, and that is delta HR, which will be equal to, when A is converting to X, then it is delta H1. X converting to Y is another step where delta H2 is the enthalpy change, and for the third step, Y converting to B, delta H3. So it will be the sum of, that is delta HR will be the sum of delta H1 plus delta H2 plus delta H3. Born-Haber cycle. It is a thermochemical cycle that shows the energy associated with each step in forming an ionic bond. Things to consider here is the electron affinity or electron gain enthalpy, ionization enthalpy for atoms which are in the gaseous state, and secondly, the diatomic molecules which need to be split up into separate atoms before reacting, where a bond dissociation enthalpy will be needed. So, when an ionic bond is formed, then depending upon the reactants, they will be needing the various type of energies like bond dissociation enthalpy, then electron gain enthalpy, ionization enthalpy, lattice enthalpy to form the ionic bond. That is called as Born-Haber cycle. Spontaneous processes and entropy. Spontaneous processes are the processes that occur, they can occur without outside intervention. They occur on its own, and these spontaneous processes may be fast or slow. For example, the combustions, they take place very fast, and conversion of diamond into graphite is a slow process. Now, entropy is now another state function, and it is defined as the measure of degree of randomness or disorderedness. Now, anything like a ice converting to liquid, water, is a spontaneous process, and the entropy change here would be positive because it is going from ordered to disordered form. So, this entropy change, measure of this disorderedness, is done by entropy. So, entropy can be measured with a calorimeter, and if it consider a perfect crystal, then it doesn't have any disorderedness. It is in an ordered form, and therefore at absolute zero, the when a perfect crystal is considered, then there is no disorder, and therefore entropy becomes is zero for that particular crystal, perfect crystal. Now, if temperature change is very small, then it can be calculated, and it is calculated like entropy change delta S will be equal to Q by T, where capital T here is the temperature at which the heat is absorbed, and Q is the amount of heat absorbed. Sum of the delta S can give total entropy at any desired temperature. The second law of thermodynamics states that the entropy of universe increases in a spontaneous process. It means now entropy of universe is actually the change in entropy of a system plus change in entropy of the surrounding. So that and that becomes delta S universe, and it is and this delta S universe is always greater than zero. That means it will be positive for a spontaneous process. So for a spontaneous process, delta S universe should be positive. It should increase. Now, if delta S system is greater than zero, that is if it is positive, and delta S surrounding is less than zero, that is negative, and it means it is non-spontaneous, then delta S universe will be greater than 0. If delta S system is non-spontaneous, that is less than 0, and delta S surrounding is spontaneous, that is very much greater than 0, more positive, then also delta S universe will be greater than 0, that is it will be positive and it will be spontaneous. So the increase in the delta S surrounding often comes from the heat released in an exothermic reaction, which means that if a system is releasing the energy, if it is an exothermic system reaction or is an exothermic, then this will go into the heat will go into the surrounding, and the entropy in the surrounding change will increase because the heat is coming from the system. So delta H system will be less than 0, that it will be negative. So when delta H system is negative and delta S surrounding is positive, then delta S universe will also be positive. That is, it is entropy of the universe will increase, or it is positive for in a spontaneous process. So for a spontaneous process, change in entropy should be positive. Gibbs free energy, denoted by delta G. It is defined as the energy associated with a chemical reaction that can be used to do work. So, Gibbs free energy change can be calculated for a reaction, and the spontaneity of the reaction can be determined. So, for a spontaneous process, delta G should be negative. At 298 Kelvin, delta G naught reaction is equal to summation of delta G naught products minus summation of delta G naught reactant. And at any temperature, delta G is given as delta H minus T delta S, where delta H is the enthalpy change, capital T is the temperature, and delta S is the entropy change. And that gives the delta G. So, four laws of thermodynamics. First, the zeroth law. If the two bodies A and B are in a thermal equilibrium with the third body, that is C, then the body A and B are also in thermal equilibrium with each other. First law, as we have already studied, delta E or delta U is given by Q minus W, where the net change in total energy of a system, that is delta U, is equal to the heat added to the system Q minus the work done by the system W. Second law, in all the spontaneous processes, the entropy of the universe increases. And the third law states that the value of entropy of a completely pure crystalline substance is zero at absolute zero temperature. Dear students, I hope you must have understood this topic. Keep learning, keep exploring. Thanks for watching. Please like, share, and subscribe to our channel for more informative videos.